Well, march we onward. It is lesson 18 in Math 221 at SUNY Geneseo. This lesson deals with linearizations, linear approximations for functions that are not linear. In this lesson, we take a look at how to use the derivative so that we can use a line to approximate something that is not a line, because as you may have remembered from your high school study, lines are really, really, really easy to use. So here's the big idea for our lesson. Differentiable functions are locally linear. And I'll give you a little something to do. If you're all by yourself and no one's around to look at you and go, what are you doing? Take your graphing calculator, graph some curvy function. Any curvy function will do just fine. And then decide for yourself that you want to pick some particular point on that function. So you graph some curvy function. Doesn't matter what that thing is, anything will do. And then you pick some special point on that curve and just zoom in over and over and over again. Just keep zooming in. And eventually what you get is a line. So it's one of these weird things with nice, smooth, curvy functions. You zoom in close enough and they're lines. So in small intervals, a function is its tangent line essentially. So in a small interval, a function and its tangent line are basically the same thing. So your author gives some equation, and the equation is the linearization equation. It's the linear approximation equation. It appears in lots of calculus books. And it says that L of x is f of a plus f prime of a times x minus a. And that's the thing that's going to appear on a bunch of index cards. It's the thing you're going to commit to memory. And I got to tell you, you already knew it. How do we find the equation of a tangent line? Well, that's y minus y1 equals x minus x1 multiplied by the slope. But what is that slope? Well, that slope is f prime at some special point. And what is that special point? Well, that special point is a. And what's the y value? Well, the y value is f of a. And so if we solve this thing for y, kick that to the other side, y is f of a plus f prime of a times x minus a, and that's the linearization equation. So if you don't want to memorize a linearization equation, good, just remember that in a small interval, a function is its tangent line. An example. Obtain linear approximations for the square root of 123 and the cube root of 123. Square root function. The square root function, that's y equals radical x, that's x to the 1/2. So I ask myself, what number has a nice square root that I know what it is that's really close to 123? And so the answer is 121. We're going to use 121. We could use any number whose square root we know, but the linear approximation is best in a small interval, so we use an a value that's close to our 123. We want to get as close as we can. So the linear approximation is f of a plus f prime of a times x minus a. Well, f of a, f of 121. So the square root of 121, that's 11. Plus f prime of a, don't know it yet, x minus 121. F prime of a. Well, if this is the f function, then its derivative is power comes down 1/2 x to the negative 1/2. And I know what negative 1/2 power means. That means it just lives in the denominator. So f prime at a, the derivative at a, that's a. Throw that 121 in there. Square root of 121 is 11. Double that, 22. So what am I looking for? Looking for an approximation at 123. This will be approximately the square root of 123. So how do I get that? I take this x value and stick it there. So that's 11 plus 1 over 22 times 123 minus 121 is 2. This number, whatever it is an approximation for the square root of 123. Similarly, we can play the game with the cube root function. The cube root function, that's x to the 1/3. Its derivative, power comes down in front. And I know what a negative 2/3 power means. It means that it lives in the denominator like that. So, well, I got to figure out what a good a value would be. So I've got to think to myself, what's a number whose cube root I know that's pretty close to 123? And that answer is 125. The cube root of 125 is 5. So the linear approximation is f of a, whoa, sorry about that, plus f prime of the, wow, sorry about that. Wow, had a small malfunction there. Okay, all better now. F of a plus f prime of a times x minus a. Well, what does that mean? F of a, that's the cube root of 125, and the cube root of 125 is 5, plus f prime of a, well, f prime of a, take that 125, throw it in there. The cube root is 5. Squared, that's 25 times 3, 75 times x minus a. 125 is a, 125 is a, 125 is a. We're interested in 123. This will be approximately the cube root of 123, and that's 5 plus 1/75 times 123 minus 125 is negative 2. This number, whatever it is an approximation for the cube root of 123. Doesn't just work with the square root function, works with the sine function. Approximates the sine of 3. 3, that's 3 radians. That's not 3 degrees, that's 3 radians. All of calculus is done in radians. So same game, same game. The function in question is the sine function. So its derivative is pretty straightforward. What a value do we use? Well, we use an a value whose sine we know and that's close to 3. So sure, sure. So what does that give us? L of x is f of a plus f prime of a times x minus a every time a is pi. So f of pi, that's sine of pi, that's 0, plus f prime of a, that's cosine of pi, that's -1, times x minus a. And so when we're interested in L of 3, that's approximately the sine of 3. That's 0 plus -1 times 3 minus pi. This number, whatever it is an approximation for the sine of 3. I'm going to give you a couple of OYOs, things to think about before we gather. One, I want you to estimate the square root of 80 using a tangent line approximation. And then two, because this is the kind of thing I might do to you on an exam or whatever, I'll let f of 0 equal 1 and let f prime of x be the cosine of x squared. Estimate f of 0.1. That gives you a decent idea of how we work with linearizations. I will see you in class.